So we have seen bunch of examples of how linear systems, and then we have seen MATLAB also. Now we will look at too many years, in my opinion, linearization, right? And then we will, if time permits, basically look at MATLAB simulation of the same, right? I'll take a bunch of examples where we have this state space representation and linearize it, right? So the nice thing about this anything polynomial, we can pretty much ignore the higher order terms, and then basically the linearization in this particular case is going to be x 1 dot equals minus 2x1 and x2 dot is equal to minus x2, and this is, we know that it's exponentially stable system, or A is Hurwitz stable linear system, right? So therefore Lyapunov indirect method, right, gives us exponential stability of the nonlinear system. And of course I have to be careful, the zero of the nonlinear system, right? So, and this is going to be very local, but and then pick some p that gives us this A transpose p plus PA less than 0. Okay, I don't mean equivalent. P that satisfies. Okay, and if we construct V of x equals x transpose px, and if I pick small enough region, basically V dot x is going to be less than 0 on that, and therefore this gives us a subset of domain of attraction. Okay, I mean basically x such that V of x less than some very small number, epsilon 1 or something like that, right? And this will give you subset of the region of attraction. Right? The question in most of the time we end up having difficulty is basically how small this epsilon 1. And we know that sufficiently small is enough, but we want to increase that epsilon 1 as much as possible, and there are methods that can be done. Right? So in a sense, basically in all the linearization example, we will get the linearization if that happens to be stable. We'll have this P matrix that produces Lyapunov function x transpose px for the nonlinear system, and once we get the Lyapunov function for the nonlinear system locally, one can actually estimate a domain of attraction, and then maximizing that estimate is actually a problem in itself. Typically in the analysis case, if we have a way of directly attacking the nonlinear system using some nonlinear Lyapunov function, that will be better. Obviously we get global results or bigger results and things like that, bigger domains of attraction, one way of thinking about is this in a control problem. Suppose if the final goal is something like this, then perhaps one can reach here and then do a local, suppose you are here and then basically draw a line to the actual destination, and then basically you can stabilize the system. How do we stabilize? Typically we'll have x dot of is equal to f of x plus, let's say for simplicity, b times u. This b could be nonlinear and things like that, and then you can choose u equals kx, and in the linear case it becomes something like a plus bk times x plus g of x, right? This is the f of x is non-linearly approximated, linearly approximated with ax plus gx, and this u is replaced by kx. So we'll end up, and we can pick my k so that even if a is unstable, this a plus bk is Hurwitz, and that gives local stability. So I'm stabilizing the system, even if this original system is unstable, I'm stabilizing it locally and around this particular point. Of course, technically I should be writing my system as with respect to this point as the equilibrium, and then basically once I'm here, instead of going to the equilibrium, I will shift my focus and then go here, and then as long as I'm within this domain of attraction, I'll try to attract myself to next equilibrium and so on and so forth, right. I'm being very loose here, and then at some point we will hopefully look at some of these ideas in more detail. But essentially in a stabilization case, basically, using this local stability with some domain of attraction, we can keep jumping between domains of attraction from one equilibrium point to another equilibrium point, and all that can be done through this U by having some dynamic equilibrium point P1, Pi or something like that, and bunch of equilibrium points P1, P2, and by changing this Pi, I keep jumping from one domain of attraction to another domain of attraction. So anyway, I mean, I won't repeat that argument anytime soon, but that's the idea, right? So in this particular case, you have this sine of x1, which we know that sine of x1 is approximately x1 for small values, right? But of course, on the other hand, d sine of x1 by dx1 is indeed cosine of x1 at x1 equals 0 produces 1. So that's the same thing as arriving at a for this scalar is 1, right? So therefore, on the whole, basically we will get x2 is going to remain x2. So that's, and then minus sine of x1 will be approximated to minus 1, and this minus x2 will remain minus x2, and then this is Hurwitz, I mean, exponentially stable, right? So this therefore the nonlinear system is, emphasizing, locally exponentially stable. Okay. Now we do know that this particular sine of x1 has multiple equilibria, so it can never be globally exponentially stable. Okay. So using nonlinear functions, one can actually show, other than that single equilibrium that we are talking about, you can actually show the domain of attraction is quite large. But when we linearize, we have to find a P that satisfies, and that's a simple enough system, and we have to find this epsilon 1 or whatever, and that gives a very small subset of the region of attraction or domain of attraction. So this example shows that basically we can still conclude local exponential stability in this particular case, but if you use nonlinear methods, we get a much bigger region of attraction. In some cases, we may not know how to do that, right? So one more example that I'll take the only nonlinear part, 1 minus x1 square times x2, and for small values of x1, 1 is much bigger than x1 square, so this is approximately x2. So I'm going to get the linear system as x1 dot is equal to x2, x2 dot is equal to minus x1 minus x2, and this is the system we have seen many times, and this is exponentially stable, right, and gives local exponential stability of the nonlinear system. Of the 0 of x dot equals f of x, the nonlinear system, right? Again, through all these examples, we linearize it and ensure that the linear system is exponentially stable, and then we get the nonlinear exponential stability. You may have seen none of the examples are going the other way, but typically they are not that interesting, because knowing linearization is exponentially stable is not as exciting as actually using the linearization method to conclude the nonlinear system. Though it's nice to know that you have this sufficient and necessary and sufficient condition for linearization, right? Now this is an example, is a bunch of examples that we're going to see are negative examples. X double dot plus g of x is equal to 0, and if I approximate g of x to be something like g of 0, g prime of 0 times x plus whatever higher order terms, right? The problem is basically this g prime of 0, even if we have this x times g of x is positive, we will end up with 0, or for that matter, maybe we will never end up with negative with this because of this condition, but this may end up with 0, and then no conclusion can be drawn. Okay, no conclusion can be drawn because the linear system will be Lyapunov stable. Okay, so unfortunately the first method, Lyapunov's first method, cannot be used in this particular case. But if you recall, basically we had something like half x dot square plus integral 0 to x g of s ds or something like that, provides, I'm going to use this term, global Lyapunov function, right? Global Lyapunov function, meaning we can show global asymptotic stability with these conditions satisfied. So this is a case where the system is stable, the linearization provides a Lyapunov stable system, and therefore nothing can be drawn, but we do have a nonlinear way of it. So this is kind of trying to convince you that sometimes linearization method may not work, but don't give up. One has to look for nonlinear systems, right? So this is another similar example. We'll end up with x1 dot equals x2 dot equals minus x1. Is this system stable? Well, I mean, let's say Vx equals x1 square plus x2 square. V dot is equal to x1 dot 2 plus 2x2 dot, and we'll get 2x1 x2 minus 2x1 x2 giving us 0, showing Lyapunov stability. And alternatively, we can see that this 0 1 minus 1 0, we know that this is plus or minus j, or where j is the square root of minus 1 as the eigenvalues, producing Lyapunov stability. So this system is, the linearization is Lyapunov stable. So nothing concrete can be drawn from the linearization. It's exactly the same example as before. So explore if we can do it nonlinear, or look at the notes. Right. So this is even worse, and I will leave it up to you to analyze. But basically, this example, we will get the linearization as x1 dot equals alpha x1, and x2 dot is 0. So either it's unstable or they are stable at most, and nothing can be concluded in terms of the nonlinear system. But look at the previous lectures, and you'll see there is some nice conclusions that we can conclude using the LaSalle's theorem. So there are umpteen number of examples where linearization utterly fails, and this is one more. And this is a case where we'll end up with x1 minus x2, x2 dot is equal to x1 plus x2, and this implies A matrix is going to be equal to 1 minus 1, 1, 1. Is this stable? Definitely not. So this is, we'll end up with one positive eigenvalue. So this will actually produce instability. Okay. So this is at least useful. Linearization happens to give a conclusion. Basically, if one of the eigenvalues is positive, then we'll end up with showing that it is unstable, right? So going on, and basically here is an example. We'll end up with x1 dot equals minus x1, and x2 dot is 0, Lyapunov stability, right? So useless. Okay. And I'm presenting all these examples because we have seen these examples in the nonlinear case, and this happens to be unstable, right? I mean, the linear system happens to be Lyapunov stable, but the nonlinear system itself is actually unstable. Okay, the same thing is true about probably the last example. We'll see. No, this actually produces a negative result. And how did I conclude that even before computing any of these things, just looking at it, basically you get this 1, 2, 2, 1, okay, and this is unstable, right? If linearization is unstable, the nonlinear system is unstable. Here is something that therefore I haven't pointed out before. So if you have a matrix A, B, C, D in the 2-dimensional, what do we need? Both real parts of has to be less than 0, right? If you know enough of linear algebra, then trace of A is lambda 1 plus lambda 2, and typically when we have real matrices, both will be complex conjugates or both real. And if both are real numbers, then I mean both are such that they are complex conjugates, the real parts will add up, will be the same thing, and both have to be negative. If both are real, both have to be negative anyway. So in either case, trace of A has to be less than 0. And the determinant is product of the two eigenvalues, and if they are complex conjugates, this will be positive, okay, by default. And if both of them are real, we know that they have to be negative, so again the product is going to be negative or positive. So in 2D cases, for A belongs to 2 by 2, A is Hurwitz, is all the real parts are negative, if and only if trace of A is negative and determinant of A is positive, okay. So for 2 by 2 systems, one doesn't have to struggle hard, we just have to check the trace and the determinant, and if one of them is positive, I mean does not satisfy this condition, then we conclude instability. So that's what I had here. The trace is positive, so trace has to be negative for stable, so I can immediately conclude that the system is stable. It so happens the determinant also is negative, which is a bad thing, right? Does it mean that it's extra unstable? I don't know, but yeah. So that's essentially the bunch of examples on the linearization, and I would invite you to basically do the same thing, except basically set up the system as your nonlinear system rather than x dot equals ax, and do this phase plot. And in each cases you will see different behavior. And one of the key things, and I'll leave that as a homework for all of you to do the MATLAB examples. What is important for you to realize in this particular case is, in all these examples you'll see stability locally, whereas when we actually try to expand it, some cases you may actually not have any issue, but in some cases you will start seeing unstable behavior. So linearization, as much as it's great, the behavior can only be shown locally, but it has also limitations. The linearization gives you Lyapunov stable, then we don't know much about it, we can't say anything about it. Only two cases that we are happy is basically either it's Hurwitz, all the real eigenvalues are real parts of eigenvalues are strictly negative, or one of them is positive. Only in that particular case we can conclude something about the nonlinear system. If it is unstable, then nice, nothing local global, it's unstable. But if it is exponentially stable, the linearization happens to be Hurwitz, then we can conclude that the nonlinear system is also exponentially stable but locally, and therefore we will have the burden of understanding how much domain of attraction we have and things like that, and then nothing can be said beyond this small domain of attraction. That is in general a problem anyway in even the Lyapunov direct method, the second method, where we have a Lyapunov function, the v dot may be satisfied only locally, right? But we have a hope for seeing something globally there, whereas in linearization method we don't have that hope. So that is essentially the linearization method using linear systems understanding. Some of the understanding of Lyapunov stability does not help much, but it's independent interest. In the next lecture or so, we will actually look at bunch of ways of constructing Lyapunov functions, and also some of the more advanced topics that I won't be going into too many details, but I will present some theorems, right? So thank you.